Hello everyone, my name is Sungwook Ryu. I'm the head of Samsung Memory Solutions Lab in San Jose. Our lab is developing future product of DRAM and SSD, including CXL DRAM, CXL SSD, and computational storage. So today, I'll talk about how the sustainability affect our memory product innovation. So this is a simple version of the system architecture, how they are evolving. Mostly architecture is swinging between decentralized and centralized. For example, early mainstream, mainframe, they trying to scale up, trying to add more and more, and end up cannot do it, so some microsystem come up with a network file system, and then they are kind of scale out. Now, they have so many computers, they cannot manage it, so they end up coming to cloud and trying to scale up. And then, because a lot of latency problem and power problem, they are trying to employ edge computing. That means scale out. So, previously, Samsung trying to support this kind of architecture, centralized and then decentralized, scale up, scale out. But now game changed. So sustainability is kind of a key element of a business, everyday business. So the point is how to provide low power solution. That's the key point. So global warming is real, and the entire industry is trying to reduce the carbon footprint. So the IT industry, that's us, we are using about 10% of global electricity, and data centers are using 10% of it. So that's the reason why we are very worried about the data centers' power consumption. So to reduce the carbon footprint, we have to employ clean energy, efficient cooling, and circular economy. In particular, servers are main power drain, so we have to focus on how to design power efficient servers to reduce the carbon emissions. So to design power efficient server, we have to consider two questions. The first one is, are we moving data efficiently? So, for example, the NVMe is optimized for 4K I/O. Now we are kind of blindly sending 4K I/O, regardless of how we are consuming the data. So if we are interested in only like 128 bytes, still NVMe, we are sending 4K bytes. That means the I/O is not efficient. Another one is we have to compare I/O cost versus computational cost. So in a local high bandwidth computer system, and then the data is, after computation, data is not reduced. It's better just send the data from storage to DRAM and compute. That may be cheaper. Another extreme is our mobile device. So we enter some data into our mobile device, and data will go through wireless network, and then WAN, and then data center. Data center has to replicate the data more than 3 data centers. And each data center has a cluster. Cluster has a rack. Rack has servers. Server has multiple SSDs. So we have, depending on the workload, we have to decide where do we have to compute, how much data we can reduce. If computing early stage is better, we have to do it. But there is no the value, then we can delay the computation. So we have to consider two questions to design energy efficient server. Now, to reduce the power consumption, unnecessary data movement should be avoided. So that means data-centric computing. So data is very valuable day by day, but even data is getting heavier. That means most of the application and services are pulling into data. So that's the data-centric computing. So data is growing, so processing data close to location is very important. So we have to consider three things: devices, interface, and architecture. So devices cases, we had two questions at my previous slide, right? We have to compare I/O versus compute. Which one is better? So computational storage, we computing at the closed data is much better. So we invented a computational storage, that's a second generation smart SSD. Interface. So some application like DLRM, the embedding table size is usually 64 byte or 128 byte, and NVMe, small I/O size is like a 4K I/O. So we invented CXL-based SSD, that's a memory semantic SSD, which support byte addressable the I/O. So we can filter out unnecessary data, and then so that we can provide less data transfer. Another one is a domain-specific architecture. Each application has a special requirement, and that application, the architecture, should be applied to broad application. I mean, we can make a very specific narrow architecture. If there is no broad application cannot use, maybe too overkill or useless. So Samsung is working with Crypto Lab for the FHE, fully homomorphic encryption project. And also we are working with Esperanto for the DLRM application. Okay, let's take a look at the computational storage. So we've been developing computational technology to process data close to its location. Our research began with the belief that in storage processing will be more important as data grows. So in this picture, if you look at the left side, this is a normal SSD process. We are reading data from NAND to the DRAM, and then send the data system DRAM, send the CPU cache, and then CPU calculate, and then store back to the result to the system DRAM. So this one has a very high data traffic and high CPU utilization. Our smart SSD computational storage, we are loading data from SSD NAND to computational module directly and calculate, and then only return calculate data to the DRAM. So we can reduce the data, the communication traffic, and also we can reduce the CPU utilization. Through this offloading computational storage, we can save the power by 7 times for the scan operation. Next one is memory semantic SSD. As I said, most of the DLRM application is accessing embedding table. Embedding table is very small, like 46 byte or 128 byte. So currently what they are doing is, if you look at the picture, the right side, so reading the 4K byte, loading to the DRAM, and then using only 128 byte or 60 byte, and then discard whole data, and then give only 128 byte to GPU DRAM, and then calculate and get the result. So this is a very inefficient the traffic operation. So memory semantic SSD, we incorporate the CXL interface. So CXL case, one packet size is 64 byte. So this one, CXL.mem interface, support the fine granular I/O. So what the memory semantic SSD is doing, we are loading data from NAND to SSD DRAM, only passing required data, 64 byte or 120 byte to the DRAM, and then GPU is getting the exact size of data to process data. So this is a very efficient data operation. So by using this, regular SSD support only 1 mega IOPS, but memory semantic SSD support 20 mega IOPS, like 20 times better for the small IO size. So memory semantic SSD, the DRAM interface, is good for small IO, but sometimes maybe a customer want to use large bulk IO, large data IO. We have a solution too. So our memory semantic SSD provide two interface, CXL.mem and CXL.io. For the NVMe bulk data transfer, we can provide, you can use CXL.io for the NVMe operation. For the memory semantic the operation, they can access the CXL.mem interface. Next one is a domain-specific architecture. So maybe you are not familiar with FHE, fully homomorphic data encryption. So this is a new technology, and if this can be usable by public, that will be a game changer. So FHE support the operation without decryption. So we encrypt the data and send the data to the cloud. Then cloud can operate apply some operation without decrypting it. In the encrypted data, we can do like a full credit card transaction validation. We can do it without decrypting the data. We can validate the input data. But the problem is it requires a lot of computation and also require larger memory space. So we are working with Crypto Lab, and then we implemented the FHE logic inside our smart SSD. So we implement the logic inside the FPGA, and then the read data from NAND directly, and then only we return result of the operation to the client, so that we can reduce the CPU utilization, and also we reduce the memory requirement of the system. Another one is DLRM application. Esperanto is a small startup. They provide thousands of RISC-V cores with very small voltage power. With only 20 watts, they can provide thousands of RISC-V cores. But the problem is data feeding. They have so powerful processors, but they are data hungry. And as I explained, DLRM case, they need a very small size I/O. So we are providing 20 mega the IOPS for this, providing that information to Esperanto. So we got a very good result for the DLRM application. So as you can see, through our innovation and collaboration with our partners, we are continually trying to develop the sustainability solution for data centers. So in this year, we have a new work stream, computational storage work stream, that will be a cornerstone for energy efficient federated data-centric computing. So with this work stream, I think this work stream can help to design power efficient servers for sustainability. And FTI itself, FTI can provide a forum, and also we can get more partners to make business cases. And also we work with competitors to build an ecosystem and also we can make a benchmark program. And academia, we need academia for the evangelization and then for the research. So we are open to work with everybody to design power efficient servers and for power efficient data centers. Thank you very much.
Thank you, Sung. Do we have questions? Yes.
Hello, thank you for your presentation. I have a question. You say that power efficient servers are sustainable, but the problem I see is if you make a server that uses half power, some customers will just buy twice as many servers because they have a certain power budget to use. So how do you see that being sustainable?
So if you look at this, for the same operation, we are using less power. So I mean, overall, server will spend a lot of power, but if you look at the same operation, how much power are you using? So with this kind of design, we can consume less power for the same operation.
I was just wondering, looking at the distance between your memory and your CPU, if you were thinking of bringing them closer and combining the processing and memory. Instead of doing in-memory computing with your hardware.
I mean, memory means DRAM or SSD?
The SSD, I mean, actually bringing people are doing computational storage where they're combining the processing with the memory so they don't have to move stuff around. Just wondered if you were looking at that at all.
Could you repeat the question? I cannot hear. I mean, what's the question?
Are you thinking of bringing the processors into the same space as the flash memory so that you're not moving data as much?
Right. So this is an example of the. In our second generation of smart SSD, we put ARM cores and FPGA, and then next version 3.0. We'll put more ARM cores and other the computation ASIC. So it'll be we'll put more compute so that we can do the computation inside the SSD. But as I said, depending on the operation, right? If there is no value, if I/O is cheaper than compute, then we have to do I/O. That means we have to bring all the data to the system DRAM and compute. But if outcome will be very small, smaller than input data, we have to compute inside the SSD. But depending on the application. So that's the reason why we have a computational storage workstream. We have to find our solution for the specific workload and use cases.
Okay, thanks very much.
Okay. Okay, thank you very much.